All right, essentially we're going to continue our discussion of equilibrium problems and how to work with them, and we're going to start by looking at special cases. One is going to be where the equilibrium constant is very, very small, and the other will be when the equilibrium constant is very, very large, and this will allow us to see kind of how we can make some approximations that will save us time, because there will be special things we can do under these situations. And then also we're going to dive into Le Chatelier's principle, which discusses how equilibrium systems adjust when they are pressured and how they relieve that stress by shifting their equilibrium position. So the first thing we want to start with is a simple equilibrium where we have a reaction going on where we have a Kc value of 6.2 times 10 to the minus 7th. This is a very small equilibrium constant, and we also know we're in a 1 liter vessel at 300 Kelvin, so about room temperature. And the 1 liter vessel lets us take the 0.25 molar that we know for each of the reactants and use it just as moles since we're in a 1 liter vessel. And so I'm going to go ahead and fill out the initial part of my ICE diagram. I know that since we're in a 1 liter vessel, there's 0.25 moles each of the two reactants, so we can see that here and here. We also know that there is 0 moles of each of the products because initially there were no products present. Next, we want to look at how they change, and this is just based on the stoichiometry of the reaction. It takes 1 C2H6 to react, so it goes down by X. It takes 3 Cl2s to react, so it goes down by 3X. And then 2 each of the products is formed, so they both increase by 2X. And so at equilibrium, we can see we have 0.25 minus X for C2H6, 0.25 minus 3X for Cl2, and then 2X for both of the products. Now, here's where we get to start making our approximation. Because this value here is so very, very, very small, this means that the products are not very favored in this reaction. The reactants are heavily favored. We make very little product. And so we're going to assume that the value of X is very, very, very small. And if that's the case, if it's small compared to 0.25, even such that 3X is small compared to 0.25, then we can make the following approximation. We can approximate that to two significant figures, the value of this does not change. So we're going to call it 0.25 for each and leave these as 2x because anything greater than 0 is significant. So we must begin to work with that. With saying that, then my Kc value for this reaction takes the two products to their coefficients as powers, so that's squared for each, divided by the reactants to their powers, so first power for C2H6, cubed for Cl2, and we know that has to be equal to Kc, which is 6.2 times 10 to the minus 7. So now I actually start subbing in my equilibrium line here. I know that each of the products is 2x, so I've got 2x squared, 2x squared. On the bottom, I've got 0.25 for C2H6, 0.25 cubed for Cl2, and so my expression becomes 16x to the fourth divided by 0.25 to the fourth power. Now, solving this for x yields me 3.5 times 10 to the minus 3 moles. And so this is a value that I am assuming is produced, or 2 times this much, is produced for CH2Cl2 and for HCl. Now, anytime we make this approximation, which generally we can make this anytime K is less than 10 to the negative third, we need to satisfy ourselves sometimes that this works. So I'm going to satisfy this for you one time, and generally this will mean that you can accept this, but I'm going to prove it to you one time. So to prove this, we're going to check our approximation of x by seeing if the value of x is 5% or less of my initial starting concentration. If that value happens to be more than 5% of my initial, then I have to go back and actually solve this equation using a quadratic with these values transplanted inside it. And that's not something that's fun to do. It's not impossible, but it's not fun, especially on an AP exam where you have very little time to solve the problem. And so down here we want to compare. 0.0035 is the value I get after estimation. And I'm going to compare that then to my original value of 0.25 and multiply by 100%. And I can see that it's only about 1.4%. So the value that I calculated was less than 5% of my original starting value. And so we're going to accept this approximation as a valid one. Again, you don't have to do this every time. I just wanted to prove to you, to yourself, one time so that you would know that it's okay to use these approximations. All right, so each of these then, if they're 2 times our value here, they're 7 times 10 to the minus 3 molar each. All right, what happens if I have a K value that's much greater than 1? So in this case, we're looking at the dissociation of nitric acid, and we know it's very exothermic. So once we return to 25C, the K value is determined to be 2.2 times 10 to the 5th, or about 22,000. So this is a very large amount of products, very small amount of reactants. If I start with the concentration of a solution of nitric acid at 0.50 molar, then determine the equilibrium concentration of molecular nitric acid in the solution. I'm sorry, I misread this. If the calculation or the concentration of the acid, that means the concentration of H plus is 0.05 molar. So this is acid meaning H plus. If the concentration of the acid is that, then how much of it still remains connected is HNO3 in the resulting solution? Well, we'll start our ice diagram where we're going to assume, in this case, when K is much greater than 1, we're going to look at the reverse reaction. We're going to assume that every bit of HNO3 dissociated, and then we're going to let it reform HNO3 and see how much it reforms. So essentially, when we do this, we pretend like we're looking at the reaction with a small k so that we can follow the same rules that we did just a minute ago. Because if the reaction to produce these two products is 10 to the 5th, then the reaction to remove them is going to be very, very small, in the order of 10 to the negative 5th or 10 to the negative 6th. So we flip it so we can treat them as a very small K reaction. And so looking at this, if I make 0.5 moles of H+, then I must also make 0.5 moles of NO3-. And again, we're going to assume, since it's not stated to me, that we're in a 1-liter vessel so that I can assume these volumes or concentrations. And so that's just stoichiometry. I make 0.5 of one, I must make 0.5 of the other also. We can also look at this and say, if they come back together to make HNO3, then I lose X amount of H plus and a corresponding X amount of NO3, so those are negative. And I'm going to produce X amount of HNO3. Now, at equilibrium, we would be 0.5 minus X for each of these, but we're going to apply the same logic we did for a very small K. Because this value is very large going forward and very, very small going backward, so going this way, K is very small, we're going to apply the approximation that says X is much less than 0.5. And because I'm assuming that, then 0.5 minus X is still about 0.5. And so that would hold true for both of those, for NO3 minus and H plus. And so essentially, we're just restating here what I told you. We're going to assume the reaction goes to completion, look at reforming products, which doesn't happen very much, and so we can ignore X for our products. And so we'll rewrite our equation like we did before. K is 2.2 times 10 to the 5th. As written, that's going to be H plus times NO3 minus over HNO3, all to the first power because they all have coefficients of 1. So then I'm going to sub in the values I know from my equilibrium line. It's always from my equilibrium line that I do this. And so I've got 0.5, 0.5 over X. And so if I solve this for X, I'll see that X is approximately 1.1 times 10 to the minus 6. And so I don't reform very much nitric acid. Now we're going to do like we did last time and prove. So I'm going to take 1.1 times 10 to the minus 6 as my X, divide it by my 0.5, multiply by 100. That's not even 1%. It's much smaller than 1%. So in this case, our approximation of ignoring that was very, very valid. There's very, very little, if any measurable, NO3 minus left. Now, if we had a very selective probe, we might be able to measure this NO3 minus. But essentially, we've converted every bit of our HNO3 over to H plus and NO3 minus, so none remains in the molecular form to speak of. And so again, this doesn't have to be proven every time you want to work one of these problems. I just proved it to you this time so that you would see it and accept that it's a valid approximation. In the future, as long as you state your assumptions, as we did up here, assuming X is much less than 0.5 or K is very small, assume 1 liter, as long as all the things are stated, you can just work the problem. As long as your K going forward is greater than about 10 to the third, you can use this approximation. And going backwards, it would need to be lesser than 10 to the minus 3. Last thing we want to talk about, it looks like Le Chatelet will have to wait for another lecture as we're quickly running out of time. Last thing we want to talk about here is the relationship between Kc and Kp. Something that's important to note, while if you're asked to give an equilibrium constant and you have both pressures and concentrations, it's up to you. You can choose whichever one you would like to choose, but they're not interchangeable. Their values are different. And so the relationship then is that Kp is going to equal Kc times RT to the delta N. And this has to do with the fact that concentration is going to be pressure over RT equals molarity. And so it's not a straight change from pressure to concentration. We also have this particular part. And so the RTs are going to change. We have to keep the pressures for Kp, but the RTs can change from product to reactant, excuse me. And so what we're talking about here with delta N, this is the change in number of moles of gas going from products to reactants. So we will subtract moles of gas in the beginning from moles of gas produced. So that if we see a positive change in moles of gas, then Kp is going to be a larger value, and if we see a smaller amount, then it will be a smaller value. And so in this case, our R and RT, R is our universal gas constant. If we're using atmospheres, that's 0.0821. If we're using kilopascals, it would be 8.31. Either of those is okay. Temperature has to be in Kelvin, as with most gas law applications. And so Kc can equal Kp under the condition that the number of moles of gas product is equal to the number of moles of gas reactant. In that case, so for example, I would have a delta N of 0, and so RT to the 0 would be 1. An example of this would be something like H2 plus I2 gas producing 2HI gas. I have 2 moles of gas here, 2 moles of gas here. So in that case, Kp could equal Kc. But in a situation where we have something like, let's see, HCO3 minus aqueous going to CO2 gas plus OH minus aqueous, this would not be. So here we would say, yes, Kp equal Kc. Up here we would say Kp does not equal Kc because we're producing a mole of gas that didn't have in the beginning. All right, Kp equals Kc times RT to the delta N is sometimes called the politically correct equation, the PC equation. This will help you remember the order of the K's. So it's always Kp equal Kc, not Kc equal Kp. So if you'll remember PC for politically correct, it will help you get them in the right order. And I'm going to stop this lecture here, and we'll proceed with Le Chatelier's as its own lecture. As I said, I'm running out of time here in my recording, so we'll stop it right here.